listen to this sentence and just, notice exactly what your brain does to understand it. The trophy didn't fit in the suitcase because it was too small. Take a second. What was too small? The trophy or the suitcase?
You probably answered that without even thinking about it, the suitcase.
Right, exactly. But notice what you just did to get there. To resolve the word it, your brain didn't just read the sentence word by word from left to right and then, immediately forget the beginning.
Right, you held the entire sentence in your mind at once.
You did. You reached back, you weighed which interpretation actually made physical sense, and you quietly delivered the answer. You basically let every single word talk to every other word.
Which is, it's a kind of reading that computers for most of the history of machine learning were just completely incapable of. I mean, they process language through a keyhole.
Keyhole.
Yeah, so by the time they reached the end of a sentence, the beginning was just forgotten entirely.
So this is a special foundational deep dive into the exact architecture behind every single modern AI system, the transformer. Our goal today is to understand it from first principles right down to the actual math.
We're getting into the weeds.
We really are, because by the end of this deep dive, you should be able to confidently explain how AI reads to, anyone at a dinner party.
It's quite a story, too. I mean, the architecture was introduced in this quiet 8-page paper published back in 2017 by 8 researchers at Google.
And its title is iconic.
It is. They titled it, "Attention is All You Need," which is a nice, very dry callback to the Beatles song, "All You Need Is Love."
I love that detail.
Yeah.
But to really appreciate what those 8 researchers actually did, we need to understand what computers were doing before 2017. Like, why was reading such a struggle for them?
Well, the dominant approach back then was the recurrent neural network, or RNN. And the logic seemed perfectly sound at the time. Language is sequential.
Right. You read a word, then the next word, then the next.
Exactly. So researchers built models that just mirrored that sequence. Word 1 comes in, the model updates its internal memory state. Word 2 comes in, it updates again.
So they basically tried to make the computer read exactly like we do, moving across the page.
They tried, but computers don't have our working memory. And this led to what's called the vanishing gradient problem.
Which is what, exactly?
Imagine reading a long paragraph, but every time you read a new word, you have to slightly erase the memory of the first word just to make room.
Oh, wow.
Yeah, so by the time the RNN reaches the end of the paragraph, the early words have been overwritten so many times, they're effectively just gone. The model forgets what the paragraph even started with.
It's the computational equivalent of constantly losing your train of thought.
Pretty much. But beyond the memory issue, there was this massive physical roadblock. Modern AI, as we know, runs on GPUs, graphics processing units.
Right, and GPUs are built for massive parallel processing. I mean, they have thousands of tiny cores that want to calculate thousands of things at the exact same moment.
And sequence completely ruins that efficiency. You just cannot process word 3 until you have totally finished processing word 2.
So running a sequential RNN on a modern GPU is kind of like putting a $1 million sports car in a bumper-to-bumper traffic jam.
That's exactly it.
The car wants to go fast, but the road forces it to crawl. So researchers simply couldn't train these older models on the entire internet because, well, doing the math sequentially just took way too long. The architectural breakthrough of the transformer wasn't just some intellectual leap. It was really about finally building software that matched the hardware.
Right. So if sequence is the bottleneck, the radically simple question becomes, what happens if we get rid of sequence entirely?
Just throw it out.
Throw it out. What if we abandon reading left to right and just let every word look at every other word simultaneously? If we go back to your sentence about the trophy and the suitcase, imagine every single word suddenly broadcasting a question to the rest of the sentence.
Like the word it, shouting, "What in this sentence am I about?"
Yes. Every word broadcasts its question, and every other word answers back with a strength based on its relevance.
Okay.
So the word it asks its question, and the word suitcase answers the loudest. The word it absorbs that context and is permanently transformed by it. It literally becomes it, which mostly refers to suitcase.
Wait, if a word is shouting a question, how does another word actually know to answer? Is it like a search engine?
It's remarkably similar to a search engine, yeah. We can break this weighing process down into 3 specific parts: a query, a key, and a value.
Okay, let's visualize that for a second. Imagine every word has these 3 components. First, the query, which is the search question the word is asking.
Right.
Second, the key, which is like a label on a manila folder it's offering to the other words. And third, the value, the actual context inside that folder.
Perfect. So when the query from one word matches the key from another word, the value gets transferred.
And that is attention, conceptually. The model is just figuring out which folders match which questions and routing the information across the sentence accordingly.
Yeah.
Exactly. I really love the folder analogy, but, and this is where we have to get into it, a GPU doesn't know what a folder is. It just crunches numbers.
Right, it's all just math.
So how do we actually translate a word asking a question into math? Because a system needs numbers to calculate this billions of times per second.
Well, it starts by turning words into vectors. And a vector is just a list of numbers.
Let's be exact here. How long of a list are we talking about?
In a model like GPT-3, every single word is mapped to a vector that is exactly 12,288 dimensions long.
Wait, 12,288 numbers just to represent one single word.
Yep. Each of those dimensions tracks an incredibly subtle aspect of the word's meaning. Is it plural? Is it an object? Does it carry a positive emotion? The model learns all these subtle numerical coordinates during training.
Okay, so we have these massive lists of numbers. How does the word it mathematically check if its search query matches the label on the suitcase folder?
To find out how similar two vectors are, we compute what's called a dot product.
Okay, let's scale that down to a simple 2D example so we can actually see how the engine turns here. Because people hear dot product and they panic.
It's really not that bad.
No, it's just basic arithmetic.
Yeah.
Imagine one vector is just the numbers 2 and 3, so 2, 3. And another vector is 1 and 4, so 1, 4. To find the dot product, you just multiply the matching positions and add them up.
Right, so you take the first numbers.
Exactly. 2 times 1 is 2.
Yeah.
Then the second numbers. 3 times 4 is 12. Then you add those results together. 2 plus 12 is 14. The dot product is 14.
And that number tells you everything. A high positive number means those vectors are highly aligned. A 0 means they have absolutely nothing in common mathematically.
So the dot product is the absolute engine of attention. It is the mathematical mechanism of checking if the label matches the question.
It is, but there is a really crucial trick here. The word's baseline embedding vector doesn't actually do the attention computation directly. The model uses learned weight matrices.
Okay, what does a weight matrix do in this specific context?
Think of a weight matrix like a specific lens. The raw word vector for suitcase passes through these lenses, which multiply the numbers to create 3 brand new vectors for that specific word. Its query, its key, and its value.
Ah.
Yeah, and this transformation is what the model actually learns during its months of training. It learns how to shape a raw word into a useful question or a useful label.
Okay, so the words have been transformed. Now we need the actual scores. We take the query of one word and we dot product it against the transposed key of another word. So Q times K transposed.
Right.
That matrix multiplication computes every single word's relevance to every other word simultaneously, in parallel.
But, and this is important, before we can actually use those relevance scores, we run into a bit of a mathematical hazard. If you multiply vectors with 12,288 dimensions together, the resulting dot products are astronomically huge numbers.
And neural networks do not handle astronomically huge numbers well.
They really don't. Big numbers create extreme confidence. If one score is 1,000,000 and another is just 1,000, the network will look exclusively at the 1,000,000 and completely ignore the 1,000. It just loses all nuance.
It gets tunnel vision.
Exactly. So we have to scale the scores down. We divide them by the square root of the key dimension. Mathematically, we write that as the square root of dk.
Scaling keeps the model open-minded. It stops the math from basically blowing up. But even scaled down, raw numbers are messy, right? Like a score of 42 versus a score of 12 doesn't immediately tell the model how to distribute the information.
Right. We need them to be clean percentages. So we apply a function called softmax. Softmax forces all those arbitrary scaled scores into readable percentages that perfectly sum to 100%.
So instead of raw numbers, the word suitcase might score 70%, the word trophy gets 25%, and everything else just splits the remaining 5%.
Which brings us to the payoff. We have the percentages. We know exactly how much each folder matters. We take those clean percentages and we multiply them by the value vector, V.
So it takes 70% of the value folder from suitcase and 25% from trophy and basically absorbs them.
Exactly. Let's put the whole mechanism together into one formula. The attention mechanism is softmax of Q times K transposed divided by the square root of dk, all multiplied by V.
Softmax of Q times K transposed divided by the square root of dk times V.
Yeah. That is the equation that built modern AI.
That is just incredible. That is the exact mathematical translation of every word asking a question and getting a folder of information in return.
It is, but the original 2017 paper realized that doing this just once per word isn't enough. Language is incredibly complex. I mean, a sentence has grammar, tense, tone, subject.
You can't capture all of that in one search.
No. So the models run multiple heads of attention in parallel. GPT-3 doesn't just do one attention check. It runs 96 heads per layer, 96 different perspectives on the text, checking for 96 different types of relationships all simultaneously.
So attention perfectly routes all this information. But attention alone isn't a functional trainable model. It needs a chassis to sit in. It needs to be assembled into a full transformer block.
Right.
But hang on, I see a bit of a hole in the logic here. If we totally destroyed sequence and every word is processed in parallel simultaneously, how does the model actually know word order? I mean, dog bites man and man bites dog contain the exact same words. Without a sequence, wouldn't they look mathematically identical to the model?
That is exactly why they introduced positional encoding. To give the model a sense of order without forcing it to read sequentially, the original paper added sine and cosine waves directly into the word embeddings.
Oh, clever.
Very clever. Modern systems use a variation called rotary positional embeddings, or ROPE-IA. But the concept remains exactly the same. The physical position of the word is mathematically baked into its meaning. A word at position 2 literally has different numbers than that exact same word at position 5.
Okay, so the words have positional encoding, they've passed notes through multi-head attention, they've gathered all this rich context. But where does the actual thinking happen? Where does the model process what all that gathered context actually means?
Well, after the attention routing, every word's updated representation flows through a feed-forward network. This is where the individual computation actually happens. Think of it like attention moves the data around, but the feed-forward network processes it.
And as you stack dozens of these layers on top of each other, how does the math not just completely collapse? I mean, we've talked about scaling earlier, but doing this millions of times seems incredibly fragile.
It is fragile, which is why they added residual connections and layer normalization. You can think of these as the statistical load-bearing walls.
Okay.
Residual connections allow some of the original unaltered data to just skip past the heavy math layers entirely, which ensures the core signal isn't lost in all the noise. And then layer normalization keeps the numbers stable at every single step.
To put the scale of this in perspective for you, GPT-3 stacks 96 of these entire blocks on top of each other. Between all those QK and V attention lenses we just talked about and the massive feed-forward networks, that single model contains 175 billion learned parameters.
It's massive.
175 billion tiny decimal point adjustments made during training to perfectly route and compute information.
And, you know, the history of this architecture taking over the world is remarkable, especially when you consider what those researchers were originally trying to do. I mean, the 2017 paper was just trying to build a better language translator, English to German, English to French. That was it.
They thought they were building a translator, but the architecture possessed a latent superpower.
It did, and Google realized it first. In 2018, they released BERT, which was a transformer trained to fill in the blanks in text. That exact same year, OpenAI released the very first of the GPT series, trained just to predict the next word.
And then the real breakthrough happened.
Yeah. By 2020, a researcher named Kaplan and his collaborators formalized what they called scaling laws. They proved that if you give this exact transformer architecture more compute, more parameters, and more data, it just predictably improves. It doesn't hit a wall like the older RNN models did.
And that endless improvement led to emergence. Basically, scaling up the models led to capabilities they were never explicitly trained for. Suddenly, a model trained just to predict the next word was writing Python code. It was doing algebra, was passing the bar exam. And even wilder, the architecture completely broke out of text entirely.
Right. By 2020, vision transformers were reading image patches the exact same way they read words. AlphaFold 2 took the architecture and applied it to biology, solving the 50-year-old grand challenge of protein folding. It turned out to be a universal pattern finder for any sequence in the universe.
So what actually happened to the original team who built it?
Well, all 8 of the original authors, who, by the way, were listed in randomized order on the paper because it was such a collaborative effort, they've all since left Google. They went on to found their own highly successful startups. In 2017, literally none of them predicted the absolute tidal wave they had just unleashed.
The Transformer won the AI race, there's no doubt.
Yeah.
But success is kind of forcing it to evolve now, isn't it? Let's look at the 2026 state of the field. The transformer has a fatal flaw.
It does. It has a massive computational cost. Because attention requires every single word to look at every other word, the math scales quadratically.
Meaning if you double the input.
If you double the length of the text you input, you don't double the compute cost, you quadruple it.
Wow. And we can't just keep building bigger power plants to run these models. So how is the field actually working around this quadratic wall today?
We're seeing incredibly clever engineering tricks. One of the biggest right now is mixture of experts, or MOE. Instead of routing every word through a massive, energy-draining feed-forward network, the model uses tiny routers. These routers send specific words to small, highly specialized subnetworks.
Oh, so instead of activating the entire brain to solve a math problem, you just route the numbers to the math department and let the rest of the brain sleep.
Exactly. It saves massive amounts of compute. Another critical breakthrough was flash attention. That's an algorithm created by Ryder. It computes the exact same attention math we discussed, but it does it without creating memory-hogging intermediate matrices. It basically reorganizes the order of operations so the GPU can process it much, much faster.
And because of those optimizations, we now have context windows that can process millions of tokens at once. I mean, you could drop an entire library of books into a single prompt today. But if quadratic scaling is a fundamental law of attention, how do we get to a point where an AI agent can track years of context? Tricks will only get us so far. We need something else entirely.
And that's why we are entering the post-transformer era. This brings in state space models, or SSMs, like Mamba, which was created by Albert Gu and Ryder. Unlike attention, SSMs scale linearly, not quadratically. They compress history in a highly efficient way, almost returning to the sequential ideas of the past, but with far superior math.
So by 2026, the absolute frontier systems like IBM's Granite V4 aren't pure transformers anymore. They are hybrid architectures. They combine state-space models for that fast linear efficiency over massive amounts of data with standard transformers for deep, rigorous attention when complex reasoning is actually needed. It really is the best of both worlds.
The architecture is constantly evolving to deal with its own limits, absolutely. But the foundation laid by those 8 researchers in 2017 remains the absolute bedrock.
Let's bring this all the way back to our opening sentence. The trophy didn't fit in the suitcase because it was too small. You now know exactly what happens when a modern AI reads that sentence. The words are converted into 12,288 dimensional vectors. They are pushed through weight matrices and transformed into queries, keys, and values.
The math happens.
Exactly. The queries and keys dot product against each other, scoring their relevance. Those scores are divided by the square root of the key dimension to prevent extreme confidence, softmax into clean percentages, and used to weight the values.
And then the result flows through 96 stacked blocks of feed-forward networks, all stabilized by load-bearing residual connections.
The boundary between sequential reading and parallel reading has been completely dissolved.
It is a profound mechanical simulation of understanding, which really leaves us with a final thought to mull over. If all of human language, all of our reasoning, our poetry, our coding, and even the complex biological folding of proteins can be successfully simulated by simply multiplying lists of numbers to find similarities, what does that actually say about how our own brains work? Are you and I just walking biological versions of multi-head attention?
Something to think about the next time you unpack a sentence.